Welcome to the API 571 Audio Masterclass series. This episode is brought to you by Mag Integrity. For the complete, high-resolution study guides, API 571 exam prep question banks, and to unlock our full private audio library, visit our premium engineering portal at magintegrity.ca.
Right, so glad to be here to get into this one.
Yeah, and whenever you're standing at the base of like a massive steel refinery vessel, and you're just looking up at all that heavy metal.
Oh, yeah, it's imposing.
It really is.
Yeah.
There is this overwhelming expectation of permanence.
Yeah.
It's solid iron, it's carbon steel, maybe heavily alloyed, but it feels indestructible.
Which is exactly what you want to feel.
Exactly. And you introduce a treatment chemical into that system specifically to scrub away the bad stuff, the harmful acid gases,
Yeah.
right? And you just naturally expect the steel to hold it. You expect the vessel to act like, I don't know, a glass holding water. It's just a barrier.
Right.
It contains the process.
Right. Because fundamentally that is the primary job of the equipment, containment. When you are operating these units, you tend to view containment as completely binary. I mean, it either holds the fluid safely or it doesn't.
Right, there's no in between.
Exactly. And as long as you are using the right, quote-unquote cleaning chemicals, you just assume you are on the safe side of that binary equation.
But then you step into the world of Amine treating, and suddenly that containment isn't so guaranteed anymore.
Oh, not at all. The rules change entirely.
Yeah. We are looking at a metallurgical landscape today where the very chemical you introduce to clean your process stream can thermally degrade and essentially turn against the system and start eating the steel from the inside out.
It really does.
It's like the immune system suddenly deciding to attack the body it's supposed to protect.
That's a great way to put it. It is the absolute definition of a hostile chemical takeover.
Yeah.
And what makes this so critical is that it happens in some of the most sensitive, high temperature, and high consequence zones of the plant.
Yeah, the worst possible places.
Exactly. Furthermore, it often occurs completely hidden from plain sight, attacking the internal surfaces in ways that can, well, actually deceive our best inspection technologies.
It's wild. So welcome everyone to this highly specialized deep dive into the specific damage mechanisms that plague our industry. Today, we are focusing exclusively and intensely on amine corrosion, specifically as it is mapped out in the API 571 documentation, Section 3.2.
Yes, Section 3.2 is where the heavy-hitting facts are.
Right. And the mission for you, sitting there listening, whether you're managing a unit, prepping for an inspection, or just trying to understand the chemistry tearing your pipes apart, your mission is to walk away with an intensive, maximum density technical briefing dossier.
We're not skipping any of the hard details today.
No, definitely not. We aren't just going to list what happens. We're going to break down exactly how and why this degradation occurs. We want to map the deep metallurgical theory directly to the harsh reality you face in the field. So, okay, let's unpack this.
Let's do it. To truly understand amine corrosion, we have to start by looking at the fundamental scientific cause. And that fundamentally revolves around the interaction between the metal surfaces of your equipment and the corrosive degradation products of the amine itself.
Okay, the degradation products.
Right. I think it's crucial to state right out of the gate, the amine, when it is fresh, clean, and operating strictly within its designed thermal parameters, it is not the enemy.
It's doing its job.
Exactly. The problem begins when the operational environment chemically alters the amine.
Right, because we need to remind ourselves what amines actually are in this context. They're essentially treatment chemicals, correct?
Yes, they are.
You introduce them into the system to perform a very specific job, which is to remove hydrogen sulfide and carbon dioxide. The acid gases, you're pulling those from your hydrocarbon streams, they are the cleaners.
Exactly. They act like a chemical sponge. So the amine solution flows through a contactor tower, contacts the sour gas, and it absorbs the H₂S and CO₂.
Right, it soaks it all up.
Yeah. But what we need to focus on is what happens when that sponge gets saturated and we need to wring it out.
Right, you can't just throw the sponge away.
No, it's too expensive. To remove those absorbed gases so we can reuse the amine, we have to heat it up in a regenerator system.
And heat is where the trouble starts, isn't it?
Precisely. The guidelines are very explicit about this. When these amine solutions break down due to excessive heat or specific operational conditions, they don't just stop working. They undergo chemical changes that create degradation products.
And these are the things that attack the steel.
Yes, these products are highly corrosive to steel. And the documentation specifies a very particular driver for this rapid degradation, which is increased carbon dioxide, or CO₂ content, specifically in monoethanolamine solutions.
MEA, right. That's what we call it in the field.
Yes, MEA. This increased CO2 loading in MEA is a direct driver of what the industry terms hot lean-amine corrosion. What's fascinating here is how the degradation products chemically alter the environment on a molecular level. Well, it turns a benign treatment chemical into a highly aggressive corrosive agent. You have this MEA solution doing exactly what you want it to do, absorbing CO2. But under the wrong thermal conditions, that rich CO2-heavy environment facilitates a breakdown of the amine molecule itself.
Wait, the molecule just falls apart?
It degrades, it forms heat-stable salts and organic acids. So suddenly, the fluid flowing over your steel isn't just a carrier for acid gas anymore. It has fundamentally transformed into an acidic, corrosive medium that actively attacks the iron matrix of the steel.
Man. So we've basically manufactured our own poison here.
Yes, exactly.
We've taken a chemical designed to protect our downstream assets from acid gas. We've overheated it in the presence of the very gas it captured and created an acid that eats the pipe holding it.
That is the tragic irony of amine systems right there.
It really is. And when this newly formed acidic soup attacks the steel, it doesn't just dissolve the metal in one uniform, predictable way everywhere, right?
No, the morphology is very distinct.
Right. The physical characteristics of the damage. When we look at how this actually manifests visually on the metal surface, we see two primary behaviors on carbon steel and low alloy steels.
Yes, the damage profiles are very distinct. The material primarily suffers from either uniform thinning in localized isolated locations, or it suffers from localized under-deposit attack.
Okay, let's break those down.
Let's look at the first one, uniform thinning in localized locations. I know that phrasing might sound like a bit of an oxymoron at first glance.
Yeah, right.
Yeah.
How can something be uniform but also localized? It sounds like saying it's completely covered in isolated spots.
Right, it's a great distinction to make. When we say uniform thinning, we mean that within a specific isolated area of the piping or the vessel, so perhaps a specific elbow, a reducer, or a particular run of pipe coming off a heat exchanger, the wall thickness is reducing relatively evenly across that specific zone.
Okay, so just in that one elbow, the whole wall is washing away.
Exactly. The surface within that zone might look relatively smooth, but the entire wall is getting thinner. It's not a single pinpoint hole, like pitting, but rather a broad, sweeping area of metal loss that is strictly confined to a particular region of the system.
While the pipe, like 10 feet upstream, might be perfectly fine.
Precisely. It's untouched.
Okay, that makes sense. It's a localized zone of uniform washout. But then we have the second type of morphology, which is localized under-deposit attack. And this one seems much more sinister.
Oh, it is significantly more insidious, largely because it happens out of sight and it accelerates rapidly.
Because of the deposits.
Right. If you have deposits forming on the internal surface of the metal, and these could be from previous corrosion products, iron sulfide scales, or other particulate matter carried in the process stream, the environment directly beneath that deposit becomes physically isolated from the main bulk fluid flow.
So the deposit acts like a little roof.
Exactly. It forms a microenvironment. The degraded corrosive amine seeps under that deposit, but because there is no fast-flowing fluid to wash it away or dilute it, the chemistry under that deposit becomes highly concentrated.
Oh, I see.
And incredibly aggressive. It creates a localized concentration cell, drilling down deep into the metal beneath it, all while the surrounding clean metal outside the deposit might remain relatively untouched.
I always think of it like a river carving out a riverbed.
That's a good visual.
Yeah, so when the water is moving smoothly over a flat, unobstructed surface, it takes a little bit of the whole riverbed with it over time. And that is your uniform thinning in a localized area. The flow is just steadily washing the surface away.
Yes.
But if there is a massive obstacle in that river, like a large boulder, or in our case, a hard deposit on the stelac, the water doesn't just flow over it evenly, it churns around it.
Right, it creates those localized flow dynamics.
Exactly. It creates high-energy eddies and concentrated flow dynamics right at the base of that boulder. It essentially drills a deep, isolated hole directly underneath and around the obstacle. That is your under-deposit attack.
The deposit isn't just sitting there.
No. It acts as a catalyst for localized fluid disruption and chemical concentration.
That analogy hits the nail on the head. The fluid dynamics and the localized chemistry work in perfect tandem to accelerate the metal loss in the exact places where you can't easily see it during an internal visual inspection.
Right, because you just see the boulder.
Exactly. You look inside, you see a bumpy deposit, and you might not realize there's a massive crater being hollowed out right beneath it.
Which perfectly brings us to the next massive piece of this puzzle. if we know this highly corrosive river is actively carving away at the containment vessel, we have to ask, what exactly is that riverbed made of?
Metallurgy.
Right. How does this specific damage mechanism interact with the metallurgy chosen for the refinery's construction? We know that certain materials are explicitly identified as susceptible to this attack in Section 3.2.
Yes, the foundational guidance on this is very clear regarding the affected metallurgy. Carbon steel and low-alloy steels are the materials fundamentally at risk here.
Okay, let's lean into the strict definitions for those materials for a moment, because it's easy in the field to just say steel, but metallurgical boundaries matter immensely when we are talking about chemical resistance.
They do. They change everything.
So what exactly constitutes carbon steel in this specific context?
When we define carbon steel rigorously, we are talking about an alloy that consists primarily of iron E with a very small amount of carbon C. The defining critical characteristic is that carbon steels do not have other alloying elements intentionally added to them to alter their core mechanical or chemical properties.
But wait, if you look at a mill test report for standard carbon steel piping, you always see a little bit of other elements, right?
Okay.
It's never just 100% iron and carbon.
You're absolutely right, and that's an important nuance. There are always trace elements. The specifications that govern these materials, like an ASTM A516 for plate or an ASTM A106 for seamless pipe, they permit small amounts of specific elements.
What kind of elements?
Well, these elements are usually artifacts of the steelmaking process or are left in because they positively affect basic properties like hardness after welding, toughness, or basic deoxidation. We're talking about small quantities of manganese, chromium, nickel, molybdenum, copper, sulfur, silicon, phosphorus, aluminum, vanadium, and sometimes boron.
Okay, but just to be clear, if I see chromium on that mill cert for standard carbon steel, that doesn't mean it's suddenly corrosion resistant.
Exactly. No, not at all. These are trace amounts, often fractions of a percent. They are not intentional, high percentage alloying additions designed to radically upgrade the chemical resistance of the base iron.
Right.
They might help the steel mill roll the plate better, but they won't stop degraded MEA from eating the pipe.
Okay, so that is carbon steel, the baseline, the workhorse of the refinery. Now, what about low alloy steels? How is that family defined, and why are we grouping it with carbon steel when it comes to adjoining corrosion?
Well, low alloy steels represent a significant step up in engineering complexity. This is a family of steels containing intentional additions of alloying elements, most notably up to 9% chromium, along with elements like molybdenum.
Okay.
The specific engineering reason we use these in refineries is for high temperature strength and creep resistance.
Just to level set for a second, creep is what happens when metal is exposed to high stress at very high temperatures over a long period, right? It literally starts to stretch and deform permanently over time.
Yes. If you put standard carbon steel in a high-temperature, high-pressure environment over years, the metal grains will slide past each other, the pipe will bulge, and eventually it will rupture. To stop that, we add molybdenum and chromium. This gives us the low alloy steels commonly encountered across refining operations. So we are talking about materials like carbon half moly, 1 1/4 chrome half moly, 2 1/4 chrome 1 moly, all the way up to 5 chrome and 9 chrome 1 moly.
And structurally, at the microscopic level, what are these?
Structurally, these are considered ferritic steels.
Ferrite, okay.
This means their crystal lattice, the way the iron atoms arrange themselves, has a body-centered cubic or BCC crystallographic structure.
Right, BCC.
While their exact microstructures might be an alteration of the standard ferrite phase found in basic carbon steel, they still share that fundamental BCC architectural framework.
Okay, I have to push back here. I really need to unpack this because it feels counterintuitive based on general industry knowledge.
Sure.
If low alloy steels are specifically formulated with up to 9% chromium, which is a massive amount compared to trace elements.
Yes, it is.
And they're specifically engineered for high-temperature service, why are they still lumped in with basic, cheap carbon steel when it comes to susceptibility to amine corrosion? Does the chromium not protect them here?
It's a great question.
Because we are always taught that chromium is the magic element that provides corrosion resistance. I mean, it's the whole reason stainless steel is stainless, right?
Yes, and that is the exact logical trap that engineers and sometimes even seasoned metallurgists can fall into when designing these systems. It is a fantastic question. You are entirely correct that in many environments, chromium imparts exceptional corrosion resistance.
Right.
It does this by reacting with oxygen to form a passive microscopic oxide layer, a shield, basically on the surface of the metal. However, the operational reality of amine corrosion highlights a critical vulnerability. Both carbon steel and low alloy steels are highly susceptible to uniform and localized thinning in this specific service.
Wait, so the chromium shield is basically neutralized, it just doesn't work?
In this specific chemical environment, yes, the shield fails completely. The specific corrosive mechanisms of hot leanamine combined with the heavy presence of CO₂ completely overpower the standard protections that we assume these ferritic structures have.
Wow.
Yeah, the chemical breakdown of the amine into those organic acids and heat-stable salts creates an environment that relentlessly attacks the body-centered cubic iron matrix. It just doesn't matter whether there is 1% or 5% or 9% chromium present.
But why does it fail, though? Why can't the chromium build its shield?
Because building and maintaining a passive oxide layer requires specific chemical conditions, usually an oxidizing environment. A hot, degraded and amine system rich in CO₂ is a very different beast.
How so?
It acts essentially as a reducing environment or a highly aggressive complexing environment where that chromium oxide layer simply cannot stabilize.
Oh, I see.
As soon as it tries to form, the corrosive soup dissolves it. The high temperature strength and creep resistance that the molybdenum and chromium provide do absolutely nothing to stop the chemical dissolution of the metal.
So you can have a pipe that is incredibly strong, that won't stretch or deform under massive high-temperature pressure, but it has zero chemical armor against this specific degrading amine solution.
Exactly. You cannot conflate mechanical high-temperature strength with chemical corrosion resistance. They are two entirely different metallurgical properties.
That's a huge distinction.
It is. In the face of severe amine corrosion, your highly expensive, incredibly strong 9-chrome-1 moly low-alloy steel might corrode and thin out just as disastrously and just as quickly as your basic off-the-shelf carbon steel.
That is a massive paradigm shift for anyone assuming an upgraded alloy automatically means an upgraded lifespan across the board.
It definitely is.
Now that we've established exactly what degrades the BCC ferritic structures of both carbon and low-alloy steels, we need to understand the precise operational environments that trigger this catastrophic failure.
Yeah.
What are the critical physical and chemical factors driving this?
Well, there are several critical operational variables that must align for this damage to occur, but the most prominent physical driver is fluid velocity and turbulence.
Here's where it gets really interesting because the API 571 guidelines give us a very specific, almost mechanical rule regarding stream velocity. It states that when the process stream velocity is low, the resulting thinning will be more uniform and widespread.
Yes.
But at locations with high velocity or high turbulence, the damage shifts. It results in strictly localized corrosion with significantly greater, much more rapid metal loss.
That is the core mechanical dynamic driving the severity of the damage. Let's think about what is happening on the surface of the steel. Even in a corrosive environment, iron will try to react with the sulfur or carbon in the stream to form a very weak, very thin semi-protective scale, like an iron sulfide or iron carbonate film.
Right.
If you have a slow, smooth, laminar flow of a corrosive degraded amine, it gently interacts with that surface. It slowly dissolves that weak scale and evenly removes layers of the steel across a large, widespread area.
So it's a slow wash.
Exactly. But the moment you introduce high velocity or turbulence, say, the fluid hits a sharp 90-degree elbow in the piping, or passes through a reduction in pipe diameter, or crashes against a weld root sticking out into the flow stream, you completely disrupt that smooth flow.
You get all those eddies.
Yes, you create shear stress against the pipe wall. That high velocity and turbulent mechanical energy continuously strips away any marginal protective scale that might be trying to form.
It's literally tearing the scab off the wound before it can heal.
That is exactly what is happening. By constantly stripping away that scale, you are exposing fresh, bare, highly reactive iron to the corrosive amine continuously.
Wow.
The mechanical action of the turbulent fluid accelerates the chemical action of the corrosion. This synergy results in deep, aggressively localized metal loss that eats through the wall thickness incredibly fast. All while the straight run of pipe right next to it might look relatively untouched because the flow there was smooth.
Unbelievable.
Yeah.
So velocity and turbulence are the physical drivers dictating where the damage concentrates. But we also have complex chemical concentration effects to worry about. We've mentioned MEA a few times, but there is a whole family of these chemicals used in the industry, right?
There absolutely is. Refineries utilize various specific chemicals in their amine treating units to remove H₂S and CO₂, and they are chosen based on the specific needs of the process.
What are the main ones?
We have DEA, which is diethanolamine. There is DGA, diglycolamine. We use MDEA, methyl diethanolamine. and of course MEA, monoethanolamine.
Do they all pose the exact same risk profile for this hot lean amine corrosion? Like, if I'm running MDEA, am I in the same boat as someone running MEA?
Well, while it is true that all amine systems require careful thermal and chemical management, the operational data explicitly calls out a very specific high-risk scenario. Increased CO2 content, specifically in MEA solutions, is the primary driver for hot lean amine corrosion.
So MEA is the outlier here in terms of risk.
Yes. In fact, if you look at the metallurgical failure analyses, specifically referencing the visual evidence often cited as Figure 322 in these engineering standards, it vividly demonstrates severe hot lean amine corrosion of carbon steel that is directly attributed to this exact condition. Increased CO2 in an MEA solution.
Why MEA specifically? I mean, why does that one fail so dramatically?
MEA is a primary amine. It is highly reactive, which makes it fantastic at absorbing acid gases quickly and efficiently.
Right, it's a great sponge.
But that same chemical reactivity means it is much more prone to thermal degradation at lower temperatures compared to a tertiary amine like MDEA. So while you must monitor all your amine systems, MEA systems with high CO2 loading have a brightly painted target on them for this specific degradation mechanism.
Which brings us to the third, and perhaps most critical, operational variable, temperature. Specifically, the time and temperature kinetics and the process limits. There's a very strict mandate regarding how hot we can run these systems.
It is an absolute operational mandate, and violating it is the root cause of the entire problem. Process temperatures must not exceed recommended limits. Period. And the reason for this is explicitly to avoid the formation of those corrosive amine degradation products we've been discussing.
Yeah.
If we connect this to the bigger picture, the temperature limit in an amining unit isn't just about the physical heat tolerance of the metal piping.
Right, because the steel can handle way more heat than the process limit.
Exactly. The carbon steel won't melt at these temperatures. The limit is entirely about the thermal breakdown threshold of the chemical amine solution itself. If you push the temperature too high, usually in an attempt to strip more gas out and increase unit efficiency, you are literally cooking your treatment chemical.
You're boiling it alive.
You are forcing the molecule to break apart into heat-stable salts, organic acids, and other highly corrosive degradation products. You are manufacturing your own corrodant inside the system.
You are turning the medicine into poison just to squeeze a little more throughput out of the unit.
Precisely. You sacrifice the long-term integrity of the physical asset for a short-term gain in chemical efficiency.
Okay, so let's pull all these variables together. We have high velocity and turbulence stripping away protective scale. We have the specific chemical volatility of MEA heavily loaded with CO2. And we have the thermal degradation that happens when we push the temperature past the safe limits.
Yes, the perfect storm.
Right. These variables don't just magically happen in a vacuum. Where exactly in the physical footprint of the refinery do we see this perfect storm occurring? Where is the real-world impact?
The highest risk profile centers strictly on the specific units and equipment where the conditions for thermal degradation and turbulence peak simultaneously.
And what specific equipment is the ground zero for this?
The absolute most vulnerable location is the piping running from the reboiler to the regenerator tower in an MEA unit.
Okay, let's visualize that process flow for a second for the listener. The reboiler is a massive heat exchanger at the bottom of the regenerator tower. Its entire job is to take the rich amine, the amine that has absorbed all the H₂S and CO₂ from the contactor, and boil it.
Exactly.
It heats it up to strip those gases out so the amine can be sent back as lean amine to do more cleaning. So, by definition, the reboiler is the hottest part of the entire amine process.
It is at maximum operational temperature. That means the risk of thermal degradation of the amine is at its absolute highest right there in the reboiler. The fluid is boiling, releasing gas, and if the temperature limits are pushed, the MEA is rapidly breaking down into corrosive acids.
And then that boiling, partially degraded fluid flows out of the reboiler through a run of piping and back into the regenerator tower to release the gases.
Yes.
And it's in this specific run of return piping that the danger reaches its peak. But the corrosion doesn't just eat the whole pipe evenly, does it? The engineering guidance gives a massive warning about a specific localized vulnerability in that piping.
Yes, the focus narrows even further. The most intense localized damage doesn't happen on the straight runs of that pipe. It explicitly emphasizes that welds are preferentially attacked.
Welds. It always comes back to the welds, doesn't it?
Yeah.
They're always the weakest link.
In this context, absolutely, and for very specific metallurgical and fluid dynamic reasons. The visual evidence of this is striking. When you review the failure data, specifically the examples often documented as Figure 321, it shows severe, violently localized amine corrosion directly at the weld in the piping, running from the reboiler to the regenerator tower in an MEA unit.
What does that damage actually look like if you were to cut the pipe open and look at it?
It does not look like rust, and it doesn't look like a gentle thinning. It manifests as a deeply carved, incredibly sharp canyon or groove running right along the internal circumferential weld seam.
Wow.
It looks like someone took a machining tool and just routed out the metal, and the severity can be staggering. Field cases frequently show this grooving going as deep as half the thickness of the material.
Half the wall thickness. Eaten away, and a highly localized line, specifically at the weld, and a line carrying high-temperature, hazardous, flammable chemical. That is a ticking time bomb.
It truly is.
But why the weld? What is it about the weld that draws the attack?
Well, it's the perfect storm of the variables we just discussed. First, the welding process creates a heat-affected zone, or HAZ, where the grain structure of the steel is altered, sometimes making it slightly more susceptible chemically.
Right.
But more importantly, the weld creates a physical profile. Even a good weld often has a root pass that protrudes slightly into the internal pipe.
Oh, it's a bump on our flat riverbed.
Exactly. It is the boulder in the river. You have the hottest fluid in the unit, heavily degraded into corrosive acids moving at high velocity. It hits that slight weld protrusion, and it creates massive localized turbulence.
So it's that mechanical stripping again?
Yes. The fluid churns, strips away any protective scale, and carves that canyon directly into the weld root. It is mechanical fluid dynamics accelerating chemical dissolution at a microstructural level.
Okay, so if this damage is eating through half this wall thickness, specifically hidden inside the pipe, localized at the welds, how do inspectors actually find it before the pipe completely ruptures? We can't just cut the plant apart to look inside. This brings us to the critical realm of in situ inspection and damage detection.
Finding this localized damage is arguably one of the greatest challenges detailed in the inspection protocols for these units.
Because it's so localized, right. To find it, inspectors rely on non-destructive testing, or NDT. And there's a very specific NDT method utilized for this. Field data points out that this specific type of highly localized weld damage was historically identified using shear wave UT or ultrasonic testing inspection.
Yes, shear wave UT. It's a staple of refinery inspection. But this raises an important question regarding how that UT data is actually interpreted by the technician in the field, because the reality of this damage mechanism reveals a terrifying inspection paradox.
A paradox. Tell me about the paradox. What's going on with the inspection?
To understand the paradox, you have to understand how shear wave UT works. You place a transducer on the outside of the pipe. It sends high-frequency sound waves into the steel at an angle, say, 45 or 60 degrees. Those sound waves bounce around inside the steel.
Okay.
If they hit a flat, smooth surface, they bounce away. But if they hit a vertical planar flaw, like a crack, the sound wave hits it flat on and bounces a massive sharp signal straight back to the transducer. The inspector sees a giant spike on their screen and says, "We have a crack."
Okay, that sounds like it's doing its job.
Here is the paradox. The localized corrosion at the weld creates such a deep, incredibly sharp groove, remember, carving out half the thickness of the metal with almost vertical walls?
Right,
Because the geometry of that corrosion canyon is so sharp and so deep, when the shear wave UT sound wave hits it, it acts exactly like a crack. The sound bounces straight back. The inspection records specifically note that because of this geometry, the shear wave UT inspection originally mischaracterized the corrosion as mechanical cracks.
Wait, seriously? Mischaracterized as cracks. So the ultrasonic wave bounces off the sharp geometry of the corrosion groove, and the signal on the technician's screen looks fundamentally identical to a crack instead of presenting as volumetric metal loss.
Exactly. Shear wave is designed to find planar defects. When it hits a broad area of uniform thinning, the signal scatters and you realize you have thinning. But because this amine corrosion creates such a sharp, localized canyon right at the weld root, the sound wave strikes the steep wall of that canyon and returns a massive, sharp echo.
Wow.
The technology is working perfectly, but the physical geometry of the corrosion is actively deceiving the interpretation of the data.
So what does this all mean? For you, the listener, whether you are the plant manager, the reliability engineer, or the inspector in the field running the UT probe, the implications of this misdiagnosis are absolutely massive. Misdiagnosing severe localized corrosion as a mechanical crack completely changes everything about how you respond.
It changes the entire risk profile and the entire engineering response.
Hmm.
If your NDT technician reports that you have a crack at a critical weld in a high-temperature amine line, your fitness for service assessment goes down a very specific, very urgent path. You are now dealing with fracture mechanics.
Right. You're assuming the pipe is going to split open violently.
Exactly. You are calculating crack growth rates, analyzing stress intensity factors at the tip of the crack, and evaluating the risk of sudden catastrophic brittle failure. A crack in a high-stress line often means you might have to shut the unit down immediately, initiate emergency procedures, and prepare for a major mechanical repair.
But if it's actually localized corrosion, if it's just a deep groove.
If it is corrosion, your engineering assessment is based on entirely different principles. You are looking at remaining wall thickness, general corrosion rates, and calculating the burst pressure of the remaining metal. It requires a completely different response.
So it's not a fracture risk in the same way.
Right. A crack might demand an immediate plant shutdown and a cut-and-weld pipe replacement. A localized corrosion groove, while serious, might be evaluated as safe to run for another 6 months with monitoring, or perhaps mitigated by applying an engineered clamp, or, most importantly, by changing the process chemistry to stop the corrosion from progressing.
The danger here is staggering. If your NDT is feeding you a false positive for cracking, you are solving the wrong problem. You might shut down a multi-million-dollar operation unnecessarily to fix a crack that doesn't exist.
Exactly.
Or worse, while you are panicking about fracture mechanics, the real problem, which is continuous catastrophic chemical thinning caused by your operations, continues to eat the pipe because you haven't adjusted the temperature of the chemistry.
That is the chilling reality check for anyone relying blindly on NDT reports without deeply understanding the morphology of the damage mechanisms at play. You have to understand what the instrument is actually seeing.
Detecting it correctly, understanding the difference between a crack and a corrosion canyon, is only half the battle. Once we know it's there, or better yet, before it even starts forming, how do we engineer this problem out of existence? We can't just keep inspecting our way to safety.
No, you can't. That leads us to the ultimate goal, which is mitigation and prevention. The engineering controls required to stop this are strict. And the most vital takeaway is that the primary defense is not a fancy new alloy. You can't just specify your way out of this with 9-chrome piping. The primary defense is operational discipline.
The core guidance states unequivocally that the most effective way to control this corrosion is proper operation of the amine system.
Yes. The methodology is entirely at the mercy of the operational parameters. If you run the system wrong, it will eat the pipe, regardless of the steel grade. The guidelines give us explicit operational mandates to prevent this. First, particular attention must be paid to acid gas loading levels.
What does that mean in practice? What happens if you overload the amine?
It means you cannot push more CO2 into the MEA than it was chemically designed to hold. If you overload the solution, you create an excessively rich acidic environment. When that overloaded solution hits the reboiler, the thermal stress causes rapid breakdown. You must respect the chemical capacity of the amine.
Got it. What's the second mandate?
Strict adherence to process temperature limits. As we discuss at length, this is the trigger. The limits exist to prevent the amine from thermally degrading into those corrosive, heat-stable salts and organic acids. If you respect the temperature limits, the amine remains a stable treatment chemical, not a solvent for your containment piping.
And the third critical mitigation.
The guidance demands proper, precise control of the reboiler rate and temperature, explicitly stating it is necessary in order to maintain proper regenerator temperatures. There is a deeply interconnected thermodynamic synergy between the reboiler and the regenerator tower.
They're essentially a single balance system.
Exactly. If operations decides to fire the reboiler too hard, maybe to strip out more gas and increase the purity of the lean amine, they push the temperatures up across the board. They intentionally degrade the amine at the heat source, and then they send that boiling, highly corrosive, highly turbulent fluid directly into the vulnerable piping leading back to the regenerator.
So if you're out there managing this unit, you have to understand that your reboiler firing rate isn't just a dial you turn for process efficiency. It is your primary defense mechanism against catastrophic weld thinning. You are the gatekeeper of the thermal degradation threshold.
You really are.
If you push for just a little more throughput by cranking the reboiler heat, you might look like a hero on the daily production report. But you might just be carving a half-thickness groove into your weld seams that will blow the unit up next year.
That is the exact unvarnished operational reality that the metallurgical failure data is trying to convey. You cannot divorce process operations from asset integrity. They are the exact same thing.
This has been a massive journey. We've covered the underlying metallurgical theory. We've broken down why susceptible BCC ferritic structures, even expensive low-alloy steels, fail under chemical attack. We've explored the critical physical drivers of velocity and turbulence and the chemical driver of thermal degradation.
We really unpacked it all.
Yeah, we've pinpointed the massive risk to the welds in the MEA reboiler to regenerator piping, unpacked the terrifying UT inspection paradox where corrosion mimics a crack, and detailed the strict operational controls required to prevent the whole disaster.
It truly is a densely interconnected mechanism. It is a place where fundamental chemistry, complex fluid dynamics, metallurgy, and daily plant operations all intersect and collide at a single, vulnerable weld seam.
Before we close out this deep dive, we want to leave you, the listener, with a complex operational puzzle to mull over. We know, based on the fundamental principles we just discussed, that high velocity and turbulence heavily dictate the severity and the exact localization of amine corrosion.
Yes.
So consider this scenario in your own plant. How might subtle future changes in your production throughput, or perhaps shifting H₂S to CO₂ ratios in a new crude feedstock you're buying, inadvertently alter the fluid turbulence profiles within a theoretically safe MEA unit?
It is a vital, forward-looking question. Could increasing your operational efficiency by slightly increasing flow rates essentially blind your current inspection plans to newly forming zones of localized attack?
Because the turbulence moves.
Exactly. If the turbulence moves because the flow dynamics change, say the eddy current shifts 2 inches downstream, the rapid corrosion moves with it. Are you inspecting the right welds today based on yesterday's flow rates?
Think about that the next time you look up at a massive solid steel vessel and expect it to just hold the fluid safely. Sometimes the physical containment is only as good as the chemistry inside it.
Very key.
That wraps up our technical deep dive on this mechanism. Don't leave your exam or your asset integrity to chance. Head over to magintegrity.ca right now to subscribe to our full premium library, download the Visual Slide Companion Pack, and master API 571. Until next time, keep your assets safe and your inspections rigorous.